On the morning of April 28th, at precisely 10:49, a secluded corner of Yellowstone National Park was disturbed by a sudden violent event. A small pool of water, simmering near its boiling point, erupted without warning. In this remote area, there were no tourists to witness the spectacle. In fact, people had been absent for nearly 2 years, ever since a boardwalk past the pool was dismantled in the summer of 2024. That decision followed a much larger explosion from the very same spot, which had hurled rocks toward onlookers. The only observer on this April morning was a webcam mounted on a remnant of that old boardwalk. What this unblinking eye recorded was the 5th such explosion from this single pool in 2026 alone. 5 events in 5 months, all from one feature. This pool, known as Black Diamond Pool in Biscuit Basin, now holds the record for the highest frequency of explosive activity ever documented for a named feature in Yellowstone's modern history. This sequence of events may be telling us something profound, a truth about this landscape that has been overlooked for 40 years. The story we are often told about Yellowstone revolves around the immense power of its supervolcano. Yet, the real and present danger, on a timescale that is meaningful to a human life, is not the magma chamber far below. It is something else entirely, a phenomenon most people in North America have never been properly introduced to. To understand this, we must first look closer at what the camera saw. The footage reveals a column of brown and grey material bursting from the water's surface. For a few brief seconds, the entire feature becomes a chaotic churn of vapor, mud, and rock, lifted clear of the ground. Then, almost as quickly as it began, the column collapses back into the basin. The pool quietly refills from the same hot spring that has fed this opening for as long as records have been kept. This was the 5th time this exact sequence had occurred in 2026, and the year was not yet half over. The April 28th event is particularly significant because it is the first of the 5 that the new webcam, part of a sensor network that did not exist 3 years ago, captured on a clear morning. The first 3 eruptions took place at night, or when the camera's lens was obscured by ice. A 4th occurred in marginal visibility, and may have been a laterally directed blast, a type of eruption with very different implications than a vertical one. Therefore, the footage from April 28th provides our first unambiguous, direct view. For nearly 2 years, this single pool has been signaling that our collective anxiety about Yellowstone may be misdirected. The true narrative of risk here is not one of a catastrophic super eruption, but of something far more frequent and immediate. The danger is a category of event known as a hydrothermal explosion. Thousands of these have occurred throughout the caldera's geological past, and they continue to happen with regularity in the present. It is a phenomenon that can occur with no warning, in places where people are often standing, and with enough energy to be lethal at close range. The recent activity at Black Diamond Pool is a perfect, small-scale example of this very real hazard. This shifts the entire framework of our questions about safety in the park. The central issue is not if the next moderate hydrothermal explosion will happen, it will. The crucial question is whether tourists will be standing in front of it when it does. This is the correct question to be asking, far more relevant to our lives than speculating when the supervolcano might erupt. To build this case, we will focus on the details of this one event, using the small story to illuminate the larger one. The 5th eruption at Black Diamond Pool, captured on a clear Tuesday morning, serves as our lens. Everything else becomes visible when you look through it. The webcam recorded the moment from an elevation of about 3 meters, looking obliquely across the water's surface. In the 12 seconds from the first disturbance to the column's collapse, a clear sequence unfolds. First, a brief, flat shudder moves across the water, the seismic energy from below arriving a fraction of a second before the main event. Then, the surface itself begins to lift. This lift is not from a single point, but rises along an arc roughly 2 meters wide on the pool's eastern side, an area understood to be the most active conduit since structural changes occurred during the 2024 event. Over the next 2 seconds, this lift develops into a vertical column, which, at its peak, reaches a height of approximately 15 meters above the pool. We know this height with precision, thanks to calibration markers placed on the basin's back wall, perfectly visible within the webcam's frame. This is the anatomy of the real and recurring threat at Yellowstone. The eruptive column is a turbulent mixture of material drawn up from below, liquid water from the pool, mud and clay scoured from the conduit's walls, and rock fragments from gravel up to the size of small cobbles. While some of these rocks are thrown beyond the pool's edge, none manage to reach the relocated boardwalk, a testament to the success of the engineering work completed after 2024. This entire display is fleeting. Over the next 4 to 5 seconds, the column gives way, collapsing back upon itself. The water cascades back into the basin and across the surrounding sinter apron, as the steam simply vanishes into the cooler air above. The system immediately begins to heal. Within minutes, the same hydrothermal plumbing that continuously feeds the pool starts to refill it. In less than an hour, to the eye of a casual visitor, the surface appears completely unchanged. But beneath this veneer of normalcy, a different story unfolds. The long-term perspective of geology reveals that the vent's geometry has been subtly altered, with its eastern side now slightly wider. Data from the YELLOWSTONE sensor shows a small but distinct shift in the temperature profile, and dissolved gas levels have changed in a manner that points to a disturbance in the shallow plumbing. Yet for an observer tracking changes over hours instead of years, the pool at sundown on April 28th would look almost identical to how it appeared at sunrise. This is the nature of a small-scale hydrothermal explosion. The event itself is over in mere seconds, leaving behind modifications to the system so subtle that only sensitive instruments can detect them. It offers no lingering signs of its occurrence. It simply happens, then ceases, and the system carries on. So why does this particular event, on April 28th, command our attention? Its significance does not lie in its magnitude. By all accounts, it was not a large eruption, ranking as one of the smaller incidents in the 2026 sequence. Instead, what makes it a crucial focal point is that it is the one event we were able to clearly see. This visual record provides an invaluable baseline against which all other data can be calibrated. The 4 other events from 2026 are, in essence, reconstructions. We know they happened because seismic and infrasound sensors recorded their signatures, and because a water level pressure transducer noted the abrupt drop and subsequent refill. Further evidence came from examinations of the surface, which revealed ejected debris in patterns that matched explosions of specific sizes and trajectories. Yet for all this data, none of those other events yielded a clean visual record. The April 28th event is the exception. Consequently, as the Yellowstone Volcano Observatory publishes its ongoing analyses of the 2026 sequence through its public channels, the April 28th event serves as the fundamental benchmark. The other 4 incidents are consistently described by how they compare to this one visible example. Our exploration, therefore, begins here. By understanding what occurred at 10:49 a.m. on April 28th, what it looked like, how it sounded within the basin, and what its signature meant for the surrounding sensor network, we can begin to grasp the essential nature of hydrothermal explosions at Yellowstone. This single, well-documented moment helps clarify why they matter, and why this small pool is now communicating a message that the park's broader geology has been trying to convey for years. Whether that message is being heard is another matter entirely, a question we will return to. But to fully comprehend the present, we must first journey back approximately 21 months to a sunlit Tuesday morning in July of 2024. On that day, a far more powerful version of the same phenomenon unfolded before some 200 tourists, their phones ready to record. That earlier explosion is what first placed Black Diamond Pool on the map, prompted the installation of the very monitoring network whose data we now study, and, more than any other recent event, reshaped public awareness of the dangers Yellowstone can present. Some of the most compelling modern footage exists purely by chance, captured by someone who happened to be holding a phone at precisely the right moment. The video record of the 23rd of July 2024 hydrothermal explosion at Black Diamond Pool is a perfect example of this. As rocks began to rain down on the boardwalk, over a dozen tourists already had their cameras aimed at the pool. Once the dust began to settle, that number had grown to nearly 50. Soon after, their videos were uploaded, edited into compilations, and amplified by the algorithms of major social media platforms. This wasn't the result of a scientific outreach campaign, but of a raw, unscripted encounter with nature's power. The term hydrothermal explosion suddenly migrated from the pages of volcanology journals into the everyday lexicon, typed into search bars by people at home, on their commutes, and in coffee shops. For a time, it became one of the most searched phrases in the geological sciences. Its entry into the public consciousness was driven by a single, visceral experience. At 5 minutes before 10, on a clear July morning, a hole in the ground erupted in a way that, to an observer standing just 40 feet away, looked as if the world itself was tearing open. The eruption occurred at 9:55 a.m. Mountain Time. The day was warm, and the skies were clear over Biscuit Basin, which held its typical morning crowd of a few hundred people. Most visitors were spread across the basin's two boardwalks, congregating near the primary attractions of Sapphire Pool and Jewel Geyser. Black Diamond Pool, however, was situated somewhat separately, located on a distinct boardwalk spur that curved around the western edge of the basin. This placement set it apart from the main cluster of features, making it a less central stop on the typical tourist path. In 2024, Black Diamond Pool was a feature that most visitors would typically overlook. It presented as a roughly circular pool, about 10 meters in diameter, its water a deep blue-green. A constant, low-volume release of gas created a gentle ripple on its surface, and a sinter apron extended for several meters from its edge. For a tourist who had already walked past the stunning blue waters of Sapphire Pool and other more dynamic geysers, it likely seemed a smaller, less remarkable version of the basin's main draws. Consequently, most people simply walked by without giving it a second thought. Those who found themselves on the boardwalk near Black Diamond Pool on the morning of July 23rd had lingered for incidental reasons. It was a matter of chance that they were there at all. Perhaps they had paused to read an interpretive sign, or someone in their party needed a moment to rest. Maybe the morning light was simply perfect for a photograph. The first indication that something was amiss was not a loud noise, but a low rumble. Eyewitnesses later described it as a hum or a vibration they could feel through the wooden planks of the boardwalk, a sensation that registered in their feet before their ears could process the sound. This subtle warning lasted for only about 2 seconds. It began with an unmistakable surge. The surface of Black Diamond Pool heaved upward, rising in an instant to form a dome of water perhaps 2 meters high. For the tourists standing nearby, this was an immediate and obvious signal of profound danger. A scramble for safety ensued. Some people dropped their phones, others, while running, kept their cameras recording. It is from these dozens of overlapping clips, captured from every angle by people fleeing in different directions, that we have a chillingly complete record of the event. They preserve the moment the dome formed, the instant it ruptured into a column of brown and grey, and the terrifying sight of rocks raining down. At its peak, the eruptive column is estimated to have reached a height of 30 to 40 meters above the pool. a truly powerful display of natural force. The entire violent episode, from the first disturbance of the water's surface to the final collapse of the column, lasted only about 30 seconds. In that brief window, the pool ejected an estimated 300 to 500 cubic meters of material, a mixture of superheated water, mud, clay, and rock. The largest of the stones thrown were 20 to 30 centimeters across. Several landed directly on the boardwalk, with one breaking a plank. Two of these rocks landed within just 5 meters of where tourists had been standing only seconds earlier. Incredibly, no one was directly struck, and there were no fatalities or serious injuries. The few minor injuries reported were from the chaotic evacuation. In a later assessment, the National Park Service and YVO researchers agreed that the absence of fatalities was purely a matter of geometry and luck. The rocks followed one path, the people another, and the two simply did not intersect. The rocks did, however, inflict significant damage on the surrounding infrastructure. The section of boardwalk closest to Black Diamond Pool was destroyed in several places, and interpretive signage was thrown clear of its mountings. With the walking surface rendered unsafe, the National Park Service closed Biscuit Basin to the public by the end of the day. By the end of the week, an official announcement confirmed the basin would remain closed until further notice. This near miss had triggered a fundamental re-evaluation. The boardwalk would need to be reviewed and likely relocated, and the USGS would work with the Park Service to install additional monitoring at the pool itself. The work that unfolded over the subsequent 21 months is what built the very sensor network whose data we are now able to study. In collaboration with the NPS and several research universities, the Yellowstone Volcano Observatory installed a level of monitoring around Black Diamond Pool that exceeds what most other features in the park have ever had. A new webcam mounted on a stable remnant of the destroyed boardwalk provides a continuous visual feed. A seismometer, placed just meters from the pool's edge, gives a detailed record of shallow seismic activity that the broader park network, kilometers away, cannot resolve. An infrasound microphone array was added to help localize the energy and direction of any future explosions. Inside the pool itself, a pressure transducer continuously tracks fluctuations in the water level, while a thermostat provides a constant stream of temperature data. This array was later enhanced in mid-2025 with a sampling line that automatically analyzes dissolved gases, searching for chemical precursors linked to hydrothermal disturbances. The boardwalk was, in fact, relocated. The new path, which is the one that remains closed to the public today, sits about 30 meters farther from the pool than the original. While the viewing angle is different, the new location creates a crucial safety buffer, one that engineering reviews determined would protect tourists from the kind of debris ejection pattern observed on July 23rd. The boardwalk has been closed to public access ever since the event, pending an assessment from YVO that the pool has stabilized. As of May 2026, YVO has not made that assessment. The reason is simple. The pool has not stabilized. The 5 explosive events recorded in 2026 alone are clear evidence of its continued volatility, raising the question of what stability even means for such a dynamic system. YVO's published analysis of the July 23rd event, which appeared in a peer-reviewed paper in early 2025, settled on a mechanism that is now the standard interpretation. The trigger was not a deep magmatic event, nor was it an earthquake elsewhere in the park. Rather, the cause was found to be a self-sealing, self-pressurizing cycle local to the conduit directly beneath the pool. It appears that, over a period of months to years, mineral precipitation along the conduit walls had been progressively narrowing the throat of the system. As this natural seal grew, the pressure of the water and steam mixture trapped in the deeper conduit increased. The water beneath the seal was at a temperature high enough that it would have flashed to steam at lower pressure, but the immense pressure was holding it in a liquid state. The failure of that seal was the critical tipping point. When the pressure from below finally exceeded the strength of the mineral deposits and the weight of the overlying water, the trapped liquid flashed to steam in an instant. The volumetric expansion from that phase change, at the temperatures and pressures involved, was on the order of a factor of 1,600. This immense and sudden expansion is what drove the entire ejection. It is what lifted the dome of water, what threw the rocks, and what produced the column of vapor and debris that soared 30 to 40 meters into the air. This single physical principle underpins so much of what we see. Everything else in the modern story of Yellowstone's hydrothermal hazard follows from that one mechanism. So, before we go further into the 2026 sequence and what the hazard rankings of Yellowstone actually say, it is vital to spend a few moments with this concept. The entire reason hydrothermal explosions are a real and recurring threat is rooted in physics, that is, at its core, almost embarrassingly simple. Hot water that wants to be steam is held under pressure by a seal. The seal fails, and it becomes steam in an instant. Multiply that by the depth, temperature, and conduit size of any of Yellowstone's 10,000 features, and you have a system that is geologically guaranteed to produce events like the ones seen on the April 28th webcam footage. The only question ever is which feature, how big, and when. With that foundation, we can now explore how a hydrothermal explosion actually works. To understand the forces at play in Yellowstone, one must visualize a column of water extending a kilometer deep into the earth, not contained in glass, but held within the intricate network of cracks, pores, and reservoirs of the rock beneath a place like Biscuit Basin. Near the surface, this water is at atmospheric pressure, bubbling and steaming as a visible spring or pool. Yet, at the bottom of this column, a kilometer down, the conditions are dramatically different. Here, the water is subjected to the immense pressure of the overlying rock and water, reaching somewhere between 200 and 300 atmospheres. This pressure increases in a roughly linear fashion with depth, creating a gradient of immense force from top to bottom. The temperature profile mirrors this gradient of pressure. While the surface water might be actively boiling at around 90 degrees Celsius, the water deep within the column is a different story. Heated by a magma chamber located another 4 to 9 kilometers below, it can reach temperatures between 250 and 350 degrees Celsius. Herein lies the fundamental principle that governs Yellowstone's geology. The relationship between pressure and temperature for water means that at these deep, hot conditions, the water should instantly flash into steam if it were at sea level, but it is not. Under the crushing weight of 200 to 300 atmospheres, the water is forced to remain a liquid, even at 350 degrees. In technical terms, it is superheated a liquid held in its state only by immense pressure. As this superheated water begins its journey up the column toward the surface, the surrounding pressure steadily decreases. At a specific depth, which varies based on temperature and water chemistry, a critical threshold is crossed. The water reaches a point where its temperature matches the boiling point for that particular pressure. From this depth upward, the water starts to boil. This is not a sudden, singular event, but a gradual, continuous process that unfolds across a zone that can be meters to tens of meters thick. As it boils, the water transforms from a pure liquid into a two-phase mixture of liquid water and steam. This mixture continues its ascent, and as it rises, more of the liquid converts to steam. By the time it nears the surface, the mixture is predominantly steam, carrying entrained droplets of water. This is the very substance we see shimmering above a hot spring or venting from a fumarole. This entire process represents the baseline behavior for a thermal feature at Yellowstone. The system finds a steady state where water rises, boils, and vents, with its surface expression, be it a hot spring, a geyser, or a fumarole, determined by the specific geometry of the underground conduits and the rate of water supply from below. This delicate balance, however, can be profoundly altered by other geological processes. The water traveling through these deep conduits is not pure. As it moves through high-temperature rock, it acts as a solvent, dissolving minerals on its journey. The water that emerges in a feature like Black Diamond Pool is therefore a chemically rich brine, carrying dissolved silica, chloride, bicarbonate, sulfate, and other species it has picked up along its path. When this mineral-laden water cools and depressurizes near the surface, its chemistry changes. Some of those dissolved substances become less soluble and begin to precipitate out of the solution, clinging to the surrounding rock. Silica is particularly prone to this process, precipitating as the water cools and pressure drops. The result is a slow, continuous deposition of minerals along the inner walls of the plumbing system. Layer by microscopic layer, year after year, the conduit accumulates silica and other minerals, causing it to gradually narrow. This seemingly minor change can have dramatic consequences. In a steady-state geyser, the system might simply adjust with a slower rise of water, leading to a different eruption cycle. But in a quiet pool, the narrowing of the conduit below can lead to a far more volatile outcome. As the throat of the conduit constricts, the depth at which boiling begins is forced upward because the increased flow resistance alters the pressure profile throughout the column. The two-phase region, where water and steam coexist, migrates closer to the surface pool. This allows pressure in the deep conduit, beneath the newly formed constriction, to build. The water trapped below the narrowing can become even more intensely superheated than the system's long-term equilibrium would typically permit. This is the essence of the seal and pressure mechanism. The mineral precipitation on the conduit walls effectively creates a slow-forming seal over a chamber of high-pressure, high-temperature water. This seal is not perfect. Water still flows through it. But it is significant enough to trap an immense amount of energy in the water below. The scale of this stored energy is staggering. When superheated liquid water is suddenly depressurized, its volumetric expansion into steam is enormous. At the conditions typical of Yellowstone's deep systems, this expansion occurs by a factor of roughly 1,600. It is a number that demands pause. 1 cubic meter of superheated liquid water at 300 degrees Celsius, upon flashing to steam at atmospheric pressure, becomes approximately 1,600 cubic meters of vapor. When this self-sealed system is multiplied across the entire volume of water trapped beneath the conduit, the potential for a violent release becomes clear. The expansion drives everything above it upward with explosive force. The water in the pool is lifted, while rocks, mud, and sediment from the conduit are caught in the blast and ejected skyward with the steam. The result is the powerful column of vapor and debris captured by webcams on April 28th and by tourist phones on July 23rd. Once the steam has expanded and the pressure is released, the system returns to a lower energy state. The conduit, once sealed, is temporarily blown open by the force of the explosion, clearing the blockage. The disturbed pool begins to refill from the deep water source below, and a period of relative calm returns. Over the following hours and days, however, the fundamental processes begin again. The conduit walls start to precipitate new layers of minerals. The seal slowly begins to reform, and the cycle prepares to repeat itself. This is the canonical mechanism for such hydrothermal explosions. It is a process born from the system's own internal physics, requiring no new injection of magma or any fundamental change deep within the Earth. A hydrothermal explosion is not an event that requires a dramatic trigger like an earthquake. Instead, its ingredients are the simple, ever-present conditions of the Yellowstone system. The innate thermal energy from below, the specific chemistry of the water, and the continuous, background process of mineral precipitation. From this perspective, these explosions cease to be unusual or special occurrences. They are an ordinary, even necessary, consequence of how this vast geothermal system functions. It is a system regulating itself, with each event acting as a periodic reset. The scale of such a reset is governed primarily by the volume of water trapped beneath a mineral seal and the depth of that seal. A shallow, small seal results in a minor event, like the one on April 28th, characterized by a brief, low plume and modest debris. A more substantial seal at a moderate depth can produce an event on the scale of pork chop geyser, with material ejected tens of meters into the air, reshaping the surface feature, as was seen at Norris Geyser Basin in 1989. And a vast, deep seal can unleash something on the scale of the prehistoric event at Mary Bay, a cataclysm that carved a crater 2.5 kilometers wide and hurled blocks for kilometers. Such an event is geologically rare, but it remains a known possibility within this system's immense power. When examined across the geological record, the hydrothermal explosions at Yellowstone reveal a predictable distribution of size and frequency, following a power law relationship much like that of earthquakes. This means that for every truly massive event, there are countless smaller ones. Minor events occur multiple times each year somewhere within the park's boundaries. Medium-sized explosions happen every few years, while large ones are separated by centuries. The most powerful events documented in the geological past have a recurrence interval measured in thousands of years. This predictable pattern provides a crucial framework for understanding the forces at play. This is the vast, ongoing geophysical process you are witnessing in the April 28th footage. The entire thermal landscape of Yellowstone, from Biscuit Basin to Norris and the Upper Geyser Basin, is merely the surface manifestation of this deep, powerful system. The event on April 28th, a plume rising 15 meters at 10.49 inches the morning, captured by a webcam on a closed boardwalk, is simply the system doing what it has always done. It is profoundly indifferent to our presence. This geological engine has been operating for hundreds of thousands of years. What has changed in 2026 is not the system, but our ability to observe it with an array of instruments that reveal its true nature. This raises a profound question. Just because we can see it with such clarity, do we truly understand what we are seeing? That is the question we will explore. Part 4. Why 5 explosions in 5 months is the anomaly. If hydrothermal explosions are a normal, baseline activity for a place like Yellowstone, a natural question arises. What makes the 2026 sequence at Black Diamond Pool an anomaly worth investigating? If the park constantly produces these events, why does a cluster of 5 explosions at a single pool over 5 months demand special attention? The answer lies not just in the number of events, but in the rate of their occurrence when measured against the historical baseline for that specific feature. Before the event on the 23rd of July, 2024, Black Diamond Pool was not considered a frequent source of hydrothermal explosions by the Yellowstone Volcano Observatory. It was known as a quiet pool. For the entire period that records exist, its observed rate of explosive activity was incredibly low, perhaps one detectable event every several years, or even once a decade, depending on the precise definition of detectable. The explosion in July 2024 was therefore the first event of any real consequence at this pool in many years. Following that initial July event, the rest of 2024 saw 2 more small explosions at the same pool in the subsequent months. These were minor enough that they would have gone completely unnoticed without the new instrumentation in place. The year 2025 brought a period of relative calm, with perhaps 2 very small events, again only identified by the sensitive sensor network and not significant enough for wide reporting. Then, 2026 began, and by the end of April, The pool had already produced 5 distinct events in just 5 months. This sudden acceleration is what defines the anomaly. A tally of 5 events in 5 months represents a rate of activity soaring to approximately 10 times the historical pre-2024 baseline for this specific pool. It is also more than double the rate observed during the 2025 recovery year. Even when compared to the latter half of 2024, when the system was still adjusting after the major July event, the 2026 rate is substantially higher. So, what could such a dramatic increase in activity signify? Within the published volcanology literature, and in communications from the Yellowstone Volcano Observatory itself, there are 4 primary interpretations for a sequence like this. Importantly, these are not mutually exclusive ideas. The true explanation for what is happening at Black Diamond Pool is likely a weighted combination of all 4. We will examine each of them in order, as each one carries different implications for what might happen next. The first interpretation, and the one most strongly supported by the available data, is the conduit modification hypothesis. This theory posits that the July 2024 explosion physically altered the underground plumbing beneath Black Diamond Pool. The blast would have cleared out material from within the conduit, changing the shape of the throat through which hot water rises. In doing so, it exposed fresh mineral surfaces to the hot, mineral-rich water. All other factors being equal, new mineral surfaces accelerate the rate of mineral precipitation, as this chemical reaction is controlled by surface area. The more surface is available, the faster minerals will be deposited. Faster deposition, in turn, means the conduit can reseal itself more quickly. Furthermore, the new geometry of the conduit, having been violently carved by an explosion rather than formed through slow, stable processes, is by its very nature far from its long-term state of equilibrium. In a system of hot, mineral-saturated fluid, a conduit that is out of equilibrium will naturally evolve back toward a more stable state through a combination of dissolution, precipitation, and mechanical erosion. This process of re-equilibration can remain elevated for years, or even decades, after a major disturbance. According to the conduit modification interpretation, the 2026 sequence is a delayed consequence of the 2024 event. It is the signature of the system finding its new, stable form. This would mean the activity is local to Black Diamond Pool, mechanistically separate from other areas in the park, and should be expected to gradually decline over the coming months and years as the conduit walls stabilize. The second interpretation is the basin reorganization hypothesis. Beneath the surface of Yellowstone, hydrothermal systems are connected in ways that are not always apparent from the ground. The geysers and pools of Biscuit Basin, including Sapphire Pool, Jewel Geyser, Blackpill Geyser, and Black Diamond Pool, along with many smaller features, all share fluid pathways deep underground. This hidden interconnectedness means that a disturbance in one area can eventually propagate to others. One interpretation suggests the basin as a whole might be undergoing a subtle reorganization of this shallow plumbing. This could be a delayed consequence of the 2024 event, or it could stem from entirely unrelated causes. In this view, the heightened activity at Black Diamond Pool is simply the most obvious symptom of a much broader, quieter shift. If this were the case, we would expect to see other subtle anomalies across the basin. As of May 2026, the Yellowstone Volcano Observatory has not reported such changes, but this does not invalidate the theory. The sensor network at other features is less dense than at Black Diamond Pool, and the ongoing analysis may yet reveal more. A third interpretation, and the one that fuels most public speculation, is the precursor hypothesis. This framework suggests that the elevated activity at Black Diamond Pool is a warning sign of a much larger event to come, either a scaled-up explosion at the pool itself or a major event elsewhere in the basin or park. However, When we look at the historical record, this idea finds little support. Major hydrothermal explosions, like those in the Pork Chop Geyser or Mary Bay class, do not consistently show a pattern of smaller precursor events in the months or years leading up to the main eruption. The July 2024 event itself was not preceded by any obvious sequence of smaller warnings. Similarly, the prehistoric Mary Bay event left no documented precursor record, as there was no instrumentation to capture it. While the precursor hypothesis cannot be dismissed entirely, it currently stands as the interpretation with the weakest empirical foundation. The data simply does not reveal a reliable pattern where small explosions consistently foreshadow larger ones. The relationship is not predictive enough to serve as a true warning. This leads to a fourth explanation, one that is undeniably a contributing factor to the apparent increase in activity: the detection improvement hypothesis. Following the events of July 2024, the instrumentation placed around Black Diamond Pool became substantially more sophisticated than what existed before. This technological leap has profound implications. A small explosion that might have occurred in 2023 at night, under a layer of ice, with no witnesses on the boardwalk, would have gone completely undetected. In 2026, however, that same minor event would be clearly registered by the seismometer, the infrasound array, and the pool level pressure transducer, even if the webcam saw nothing. Therefore, the higher rate of events we see today partly reflects our enhanced ability to count smaller occurrences that were previously invisible. YVO's own communications acknowledge this caveat. An unknown fraction of the increase is simply a detection effect, not a true rise in geological activity. Determining the precise balance between a real elevation in activity and this detection improvement requires more analysis than has been published so far. There is also a fifth consideration that, while not a full-fledged interpretation, is an essential part of an honest assessment: genuine stochastic variability. All natural systems, including Yellowstone's hydrothermal network, are subject to random fluctuations. The rate at which events occur at any given feature is not constant. It fluctuates around an average, and these fluctuations are a normal part of the system's behavior. A cluster of 5 events in 5 months, against a historical background of perhaps 1 event every few years, is certainly unusual. Yet, it is not necessarily statistically impossible by chance alone. The Poisson distribution, which describes the timing of random events, allows for such clusters to occur at rates far higher than the long-term average, simply because random arrivals are not evenly spaced. It is possible that some of the apparent increase at Black Diamond Pool is a true change in the underlying rate, while some is merely a chance fluctuation. To disentangle the two requires more data, which is precisely why the sensor network continues its patient vigil. So, which of these explanations is the correct one? The most honest answer is that the truth is likely a weighted combination of them all. The conduit modification interpretation is almost certainly the largest contributor, with the basin reorganization theory, the detection improvement effect, and stochastic variability all playing a part. The precursor interpretation, however, likely contributes very little, if anything. This combined understanding informs the trajectory that the Yellowstone Volcano Observatory is publicly working from. The expectation is for continued small events at Black Diamond Pool over the coming months and years, followed by a gradual stabilization as the conduit finds a new equilibrium. No escalation to a larger event is anticipated, and no propagation to the rest of Biscuit Basin is expected. The continued closure of the basin to the public serves as a precaution against the small but non-zero residual risk that a larger event could occur. This entire assessment is grounded in the available data and is consistent with the published volcanology of hydrothermal systems. But more importantly, it is the very hypothesis that the entire monitoring network around Black Diamond Pool was built to test. The reason a webcam is pointed at that pool, a seismometer is buried in that basin, an infrasound array sits on that boardwalk remnant, and a dissolved gas sampler is in that water is to watch for the unexpected. If the trajectory shifts, if YVO's interpretation proves to be wrong, if the basin reorganization scenario begins to produce detectable anomalies at other features, or if the precursor model suddenly becomes the correct one, the sensor network is designed to see it before the public does. That is the fundamental purpose of the instrumentation. Its goal is not to confirm what we already think, but to detect any deviation from our current understanding and to provide enough warning to mitigate the consequences of being wrong. This entire, multi-layered picture leads to a conclusion that bears repeating. The 2026 sequence at Black Diamond Pool is not, by itself, a precursor to anything dramatic. Instead, this system is showing us, in real time, the very category of event that the public's understanding of Yellowstone has largely failed to account for over many decades. The question of what truly makes Yellowstone dangerous, the authentic threat that lies at the heart of our exploration, does not begin with its famous magma chamber. It starts right here, with a small, unassuming pool that has now erupted 5 times in just 5 months. To grasp why the public perception of this threat profile is essentially inverted, we must examine what the USGS itself communicates about the hazard rankings across the entire park. What becomes clear is that the official scientific consensus and the popular narrative are not the same, and the gulf between them represents one of the more significant, if quiet, failures in science communication concerning American geological hazards in modern times. Part 5. The official USGS hazard ranking. If you were to sit down in the year 2026 and review the official United States Geological Survey assessment of hazards at Yellowstone National Park, you would find a document that might seem quite surprising, especially if your knowledge has been shaped primarily by popular media. The report in question is the latest version of a hazard framework that first appeared in the Christensen et al. Assessment from 2007. This framework has been consistently refined through subsequent USGS bulletins, with the most recent edition incorporating data from monitoring upgrades completed after 2024. This comprehensive document serves several key functions. It catalogues the types of hazardous events possible at Yellowstone. It organizes them by their relative probability on a human-relevant timescale, and it projects the consequences should any of these events occur. It provides a clear, data-driven hierarchy of risk that stands in stark contrast to common belief. The official ranking, from the most probable to the least, unfolds like this. First on the list are large earthquakes. This is not because Yellowstone is uniquely prone to seismic events, but rather because the park is situated within the expansive intermountain seismic belt. Furthermore, the historical record includes the 1959 Hebgen Lake event, a magnitude 7.3 earthquake, whose epicenter was just outside the caldera, but was fundamentally a Yellowstone region event by any meaningful measure. Based on historical data and active fault mapping, the annual probability of a magnitude 7 or greater earthquake occurring in or near the caldera is estimated to be on the order of 1 in several hundred years, making it the most likely major hazard. Second are hydrothermal explosions, the very category we have been observing. The yearly probability of a pork chop scale or larger hydrothermal event somewhere in the park is about 1 in a few decades. This represents a likelihood that is roughly an order of magnitude greater than a caldera-forming eruption. When weighted by consequence, the difference is even more stark. While a super eruption would be a continental catastrophe, even moderate hydrothermal explosions can be lethal at close range and can reshape the park's surface, forever altering the visitor experience. Third in the hierarchy are lava flows. Yellowstone has indeed produced lava flows in its post-caldera history, with the most recent geological evidence dating back approximately 70,000 years. These flows are characteristically slow, posing little direct danger to anyone who can walk away. In modern Yellowstone, their primary impact would be on the park's infrastructure rather than on human life. The annual probability of such an event is estimated at roughly 1 in 100,000 years, when considering all possible vent locations. Fourth are small to moderate explosive eruptions. These events involve magma breaking the surface with explosive force, but on a scale vastly smaller than a caldera-forming event. Such eruptions have occurred in Yellowstone's past, but they are even less common than lava flows, with an annual probability in the range of 1 in several 100,000 years. Finally, at the very bottom of the list are the caldera-forming super-eruptions. Their annual probability is exceedingly low, on the order of 1 in 700,000 years. This is the category that the public's imagination treats as the primary Yellowstone hazard, yet in the official ranking, it is the least likely scenario by a very significant margin. To truly appreciate the scale of this disparity, it is crucial to understand what these numbers mean, as the spread between them is the entire point. The annual probability of a magnitude 7 or greater earthquake at Yellowstone is roughly 1 in several hundred. In contrast, the annual probability of a caldera-forming eruption is about 1 in 700,000. The ratio between these two likelihoods is on the order of 1,000 to 1. This means a major earthquake is approximately 1,000 times more likely to happen in any given year than a supereruption. Hydrothermal explosions, when integrated across all basins, fall somewhere in between these two extremes, but are much closer to the frequency of earthquakes, with multiple events of varying sizes expected per decade. The data paints a clear picture of where the most immediate risks lie. And yet, if you were to stop 100 people on any street in the United States and ask them about the great danger of Yellowstone, the vast majority would describe something related to a super eruption. They might claim it is overdue, that the magma chamber is rapidly filling, or that the government is concealing the truth. These ideas have become deeply embedded in our collective consciousness, but none of them align with the available scientific data. The reality is that the magma chamber is not expanding in a manner that would indicate an imminent eruption. The notion that an eruption is overdue is not technically meaningful, because the recurrence interval between past events has too much variability, and the sample size of eruptions is too small to build a reliable, predictive framework. And the idea that the government is hiding this information is simply not plausible. All of the underlying data is open source, continuously analyzed by researchers around the world, including scientists outside the US, who have no incentive to conform to any single government's narrative. This transparency is a cornerstone of modern geoscience. This brings us to the great inversion. The public has been conditioned by decades of documentaries, news reports, and dramatic films to fixate on the single least likely category of hazard at Yellowstone. In doing so, we have paid virtually no attention to the second most likely category, the very one that is most probable to actually cause harm to a tourist on any given day. The power of a dramatic story has, it seems, overshadowed the more mundane but far more relevant reality. The sequence of events at Black Diamond Pool in 2026 is, in its own quiet and persistent way, creating a visible record of the very hazard category that the public has been ignoring for so long. The explosion on April 28th is, in terms of its size, almost a perfect match for the kind of event that the USGS Hazard Assessment ranks as most relevant to human harm at Yellowstone on the scale of a human lifetime. It is the canonical, real-world example of the second item on that official list, a tangible reminder that the Earth speaks in more than just cataclysms. While the public's mental model of Yellowstone often fixates on one particular hazard, it tends to bypass a far more probable one. If a visitor to the park were to face a life-threatening geological event during their lifetime, say, while walking the boardwalks on an ordinary Tuesday morning, it would almost certainly not be a super eruption. The true and most immediate danger is an event much like the one witnessed on April 28th. This is the genuine hazard. A hydrothermal explosion that erupts when a boardwalk is open, in a basin filled with tourists, and throws debris in a pattern that intersects with where people are standing. It is this specific type of event that the data identifies as the most relevant risk, a reality powerfully demonstrated in a single moment by the footage from that day. To understand this inversion of risk, we must turn to the numbers, for it is here that the gap between perception and reality becomes undeniable. The United States Geological Survey, or USGS, provides a current hazard assessment that lists the annual probabilities for each category of geological event at Yellowstone. When we place these figures side by side, a much clearer and perhaps surprising picture of the park's dangers begins to emerge. This data allows us to move beyond abstract fears and into the concrete language of statistics. Let's begin with the event that captures the most attention. The annual probability of a caldera-forming supereruption at Yellowstone is estimated to be approximately 1 in 700,000. As a decimal, this is a vanishingly small number, roughly 0.000014. Over the span of a century, the likelihood of witnessing such an event rises to only 1 in 7,000. The average time between these massive eruptions, known as the recurrence interval, is somewhere between 600,000 and 800,000 years. Given that the last supereruption occurred about 630,000 years ago, we are indeed within the typical range. However, framing this as being overdue is not statistically sound. The geological record shows significant variability, and the sample size of past events is too small for precise prediction. The honest assessment is that the rate is low, and we are simply within the broad, typical window, neither obviously due for an eruption nor statistically safe from one. Now, consider the probability of a major earthquake. The annual likelihood of a magnitude 7 or greater tremor occurring in or near the Yellowstone caldera is on the order of 1 in 300 to 1 in 500. The exact figure depends on the specific fault mapping and historical analysis used. This means that over a 100-year period, there is a 20% to 30% chance of such an event occurring. Within 1,000 years, it becomes overwhelmingly likely. This is not a theoretical danger. The historical record includes the 1959 Hebgen Lake event, which triggered a landslide that tragically killed 28 people. More recently, the 1975 Norris earthquake, a magnitude 6.1, caused significant damage and altered the behavior of several geothermal features. These events, occurring within living memory, are tangible demonstrations of the seismic power the system can unleash. Next in our comparison are hydrothermal explosions, on a scale comparable to or larger than the 1989 Pork Chop Geyser event. When integrated across all of Yellowstone's basins, the annual probability is on the order of one event every few decades. This suggests that over a 100-year time frame, we should expect somewhere between 3 and 10 such explosions. In 1,000 years, that number rises to between 30 and 100. This is consistent with what has been observed. Over the past 150 years of relatively continuous observation, the park has recorded a dozen to 24 events, large enough to leave clear evidence, aligning with a recurrence interval of roughly one event per decade somewhere in the vast park. At the most frequent end of the spectrum are smaller events, like the one at Black Diamond Pool, which involve localized debris ejection limited to the immediate basin. When tallied across all the active features in the park, The probability of these events is on the order of 1 to several occurrences every single year. The primary reason most of these go unnoticed is that they happen at features without dense instrumentation, in basins where boardwalks are far from the action, or at times when no one is present to witness them. The 2024 event was not statistically unusual for the park as a whole. What made it extraordinary was the convergence of its size, its location near observers, and the presence of tourists with phones who captured it. Without any one of those three factors, the event would have likely remained an unrecorded geological footnote. Placing these numbers next to each other reveals the stark inversion of risk. Each year at Yellowstone, the expected number of magnitude 7 or greater earthquakes is about 0.003. The expected number of pork-chop-scale hydrothermal explosions is around 0.03. The expected number of black diamond-scale explosions is between 1 and 5. And the expected fraction of a caldera-forming supereruption is a mere 0.000000014. This means the ratio of expected small hydrothermal explosions to expected supereruptions per year is on the order of 10 million to 1. It is a staggering comparison that demands we re-evaluate our focus. Within that 10 million to 1 ratio lies a deeper point about human perception. A number of this magnitude is something the mind is not built to intuitively grasp, and it's a reality the public conversation around Yellowstone has struggled to accommodate. When presented with such a vast number, the brain tends to simplify, sorting possibilities into two basic bins: things that happen and things that do not. A caldera-forming eruption lands in the things that happen bin simply because the word eruption is familiar. In contrast, the term hydrothermal explosion is less familiar and carries less weight. In our minds, the 10 million to 1 frequency ratio collapses into a much smaller, more manageable perceived difference. We end up feeling that both events are roughly in the same category of likelihood, causing us to fixate on the dramatic story while underestimating the actual, more frequent one. This disconnect is not just a hypothesis, it is a documented phenomenon. A 2018 study on the public perception of Yellowstone's hazards, conducted by researchers at several US universities and cited in USGS outreach materials, confirmed this very issue. The study found that the dominant mental model among the general public was, by far, the caldera-forming supereruption. For most respondents, the far more common and immediate risk of a hydrothermal explosion was not part of their mental model at all, revealing a profound gap between scientific understanding and public awareness. When surveyed about the dangers of Yellowstone, many people have never even encountered the term hydrothermal explosion. In studies asking the public to rank various hazards, the famous supereruption is consistently placed first, while hydrothermal explosions are ranked last or near the bottom. This perception is the exact opposite of the official hazard assessment from the USGS. What is particularly unsettling, however, is what happens when people are presented with the correct information. Research shows that after being told the actual rankings and the data behind them, most participants will update their stated beliefs. But when surveyed again just weeks later, their original mental model has typically reasserted itself. The supereruption is simply a more powerful and memorable story, one reinforced by countless films and documentaries. It has a name and a narrative that is easy to grasp. A hydrothermal explosion, by contrast, is a clinical phrase, difficult to visualize and hard to integrate into a mental framework already built around the supervolcano. The footage of Black Diamond Pool's 2024 event offered a rare opportunity to change this. For the first time, the phenomenon of a hydrothermal explosion had a piece of viral media attached to it. Following the July 23rd event, online search interest in the term skyrocketed. People who had never heard the phrase were suddenly typing it into search engines, leading to a flurry of articles and podcast discussions. The term began to enter the popular vocabulary. Yet, this newfound awareness did not translate into a deeper, structural understanding. The public conversation largely failed to grasp why these explosions are the more probable hazard, how they differ from magmatic eruptions, or what it truly means that a super eruption is the least likely event. The footage was treated as a fascinating curiosity, an interesting tangent to what was still considered the main Yellowstone story, the supervolcano. The fundamental lesson that the most immediate threat is not what most people have been led to believe did not land. The sequence of events in 2026 represents a second chance. Witnessing 5 separate explosions at the same pool within 5 months, including the April 28th event captured in clear morning light by a webcam, provides an opportunity to finally deliver the structural lesson that the 2024 event could not. Whether this opportunity succeeds depends almost entirely on how the story is framed, who tells it, and whether it can avoid being caught in the same algorithmic and editorial loops that process all Yellowstone news as a side note to the supervolcano narrative. The video you are watching is one attempt to frame it correctly. On its own, it will not be enough. But the scientific data has been pointing in this direction for 40 years. The empirical record now unfolding at Black Diamond Pool provides, in real time, the kind of demonstrable evidence that data needs to be heard. The numbers are not ambiguous, and the hazard ranking is not contested by any serious researchers. The footage exists, the pool is still active, the opportunity to tell the right story is directly in front of us. And yet, public perception research suggests we are likely to handle it poorly, but the likelihood of mishandling the story is not the same as an inevitability. The data says what it says, and the actual Yellowstone threat is what it is. In the meantime, the pool will probably explode again before the year is out, at a date and time the sensor network will record, and which a webcam may or may not capture, depending on the weather. That event will once again give us a brief opportunity to look at what is actually dangerous about this place. To understand why Black Diamond Pool, out of all the thousands of thermal features in Yellowstone, is the one producing 5 explosive events in just 5 months, we need to explore the basin it resides in. This brings us to the geology and history of Biscuit Basin. Biscuit Basin is a small but significant thermal area on the west side of Yellowstone's Upper Geyser Basin region, located only a few hundred meters west of the Old Faithful complex. It sits within the Yellowstone caldera, specifically in its southwestern quadrant. The basin rests on a substrate of glacial and lake sediment, which in turn overlies rhyolitic volcanic rocks emplaced during eruptions that occurred in the hundreds of thousands of years after the caldera formed. The basin's unusual name comes from biscuit-shaped sinter deposits that once surrounded its larger features. In the early 20th century, before the park's protection policies became more rigorous, many of these formations were broken or taken by visitors. While most of the original biscuits are gone, the name persists. The basin contains a rich variety of geothermal features. Its largest and most famous is Sapphire Pool, a hot spring with stunningly blue water on the basin's eastern side. Sapphire Pool underwent a dramatic transition in 1959, immediately following the Hebgen Lake earthquake. Although the quake's epicenter was outside the caldera, its seismic energy propagated across the entire region, triggering changes in many of Yellowstone's geysers. Before the earthquake, Sapphire Pool was a relatively calm spring. Afterward, it became violently energetic, with eruptions throwing water tens of meters into the air and its surface boiling intensely. The connection between earthquakes and changes in hydrothermal behavior, even at distances of tens to hundreds of kilometers, is well documented, and the transformation of Sapphire Pool is a canonical example cited in introductory volcanology textbooks. Other named features in Biscuit Basin include Jewel Geyser, which erupts every 5 to 10 minutes to a height of about 6 meters, and Black Pearl Geyser, which has cycled through periods of activity and dormancy over the past century. Before the 2024 event, however, Black Diamond Pool was not on most visitor itineraries. It sat on a secondary spur of the boardwalk, away from the main loop, and most visitors walked past it without paying it much mind. In 2023 and earlier, its surface was a more or less continuously calm pool of blue-green water, with only slight ripples caused by low-volume gas emissions. By all appearances, it was a quieter and less impressive cousin to Sapphire Pool, located across the basin. The water that emerges in all of Biscuit Basin's features is meteoric in origin, sourced from the rain and snow that fall on the region. The journey of water in this remarkable landscape begins as rain and snow falling upon the vast Yellowstone Plateau. From there, it embarks on a slow subterranean odyssey, percolating through volcanic rhyolite rock over years, sometimes even decades. This water descends to profound depths, perhaps several hundred meters to as deep as 2 kilometers. Down in the earth, it is superheated by the immense thermal energy of the underlying magma chamber and residual hot rock from ancient intrusions. Eventually, this energized water ascends once more, channeled through a network of faults and fractures until it emerges in the geyser basins at the surface. The water that surfaces in Biscuit Basin, like much of the Upper Geyser Basin, carries a distinct chemical signature. It is predominantly alkaline chloride, with a pH just above neutral. It is also rich in dissolved silica, chloride, sulfate, and a variety of trace elements. This chemical profile tells a story, distinguishing it from the more acidic waters of Norris Geyser Basin or the sulfate-heavy waters near Mud Volcano that create acid-altered ground. In essence, the water's chemistry is a liquid diary of its journey, revealing the rocks it has touched, the temperatures it has endured, and the depths it has visited. Deep beneath Biscuit Basin, a complex geological engine is at work. The reservoir that feeds the surface features resides at depths ranging from several hundred meters to about 2 kilometers. Far below that, between 5 and 10 kilometers beneath the caldera floor, lies the magma chamber itself, the ultimate source of the region's heat. The zone between this deep magma and the water reservoir is filled with intensely hot rock, a legacy of past volcanic intrusions over hundreds of thousands of years, which continues to be warmed by the magma's presence. Within the deep reservoir, water reaches temperatures between 250 and 350 degrees Celsius. At these depths, the immense pressure is enough to keep the water in a liquid state, despite being far above its boiling point at sea level. However, as this superheated liquid rises through conduits toward the surface, the pressure rapidly decreases. This change forces a dramatic transition, where the water flashes into a turbulent mixture of liquid and steam, ultimately emerging at the surface as the powerful displays we witness. Biscuit Basin is no stranger to powerful hydrothermal activity. It possesses a documented history of explosions that extends far into the prehistoric record. The very surface of the basin and its surroundings bear the scars of this past, showing evidence of ancient explosion craters and fields of ejected debris. More recently, Sapphire Pool was known to have produced small, documented explosive events following the 1959 Hebgen Lake earthquake. Even Black Diamond Pool, prior to its notable 2024 event, had a history of producing small, irregular explosions over the preceding decades. From a volcanological perspective, the basin is a known and active site for hydrothermal explosions. What made the 2024 event so significant was not the nature of the activity itself, but its sheer magnitude and visibility at one particular pool. The specific location of Black Diamond Pool within the basin is geologically crucial to understanding its behavior. The pool lies directly upon a structural lineament, which is essentially a small fault line that traverses the basin from northwest to southeast. It is no coincidence that several of the basin's most active thermal features are situated along this very line. In hydrothermal systems, fault zones are natural superhighways for fluid flow. The fractured rock along a fault offers much higher permeability than the solid rock surrounding it, allowing hot water from deep below to ascend more easily. This easier flow translates directly to more active features at the surface. The fact that Black Diamond Pool sits on this lineament helps explain why it is consistently one of the more dynamic features in the basin and why it is so responsive to geological perturbations. The 2024 event physically altered the local geology of Black Diamond Pool, and subsequent surveys have documented these changes in detail. The pool's vent, the opening at its bottom through which water flows, was noticeably widened. The conduit system beneath the pool was partially scoured of accumulated mineral deposits. Furthermore, the sinter apron encircling the pool was disturbed by the force of the ejection, and new cracks formed in the aftermath, some of which are now visible from the relocated boardwalk. While none of these modifications were severe enough to fundamentally change the pool's essential character, they collectively shifted its local geometry. The pool was pushed away from its long-term state of equilibrium and into a new, less stable condition, which has directly led to the sequence of smaller events observed in 2026. As of May 2026, the other features in Biscuit Basin have shown no obvious changes that would suggest a widespread, basin-wide reorganization. Sapphire Pool is behaving much as it has since the post-Hebgen Lake era. Jewel Geyser continues to erupt on its relatively predictable schedule, and Black Pearl Geyser is currently in one of its quieter phases. Observed through the sensor network and visual records, the basin as a whole appears largely unchanged from the year before the 2024 event, with the singular exception of Black Diamond Pool. This lack of broader change strongly supports the interpretation that the 2026 sequence is the result of a localized conduit modification at Black Diamond Pool, rather than a more concerning basin-wide shift, which would likely manifest as changes at multiple features. Of all the thermal features in Biscuit Basin, Black Diamond Pool is, by a significant margin, the most heavily instrumented today. The combination of a seismometer, an infrasound array, a water level pressure transducer, a temperature thermistor, a dissolved gas sampler, and a webcam represents a level of monitoring that few, if any, other named features in the entire park have ever received. This means that our knowledge of the 2026 sequence at Black Diamond Pool is characterized by a precision that is highly unusual in the history of Yellowstone monitoring. The sequence has been captured in a degree of detail that was simply not possible for earlier explosive events at other features in the park's long history. If this same series of events had occurred at Sapphire Pool, Black Pearl, or any of the dozens of less instrumented features, our understanding would be far more limited. The public would know that explosions had taken place, but the specifics would be lost. We would not know the precise second each one happened, what their seismic and infrasound signatures were, how the water level changed in the moments leading up to an eruption, or how dissolved gas concentrations fluctuated. We would be left with rough counts, post-event surface observations, and a vague sense that something was happening. Because of where it is and the technology installed there after 2024, the Black Diamond Pool sequence is generating a level of empirical detail that is a profound new resource for the broader study of Yellowstone's hydrothermal explosions. This naturally brings us to the question of scale. The 2026 events at Black Diamond Pool are small. The 2024 event was larger, but still confined locally. To truly put these into context, We must look at the upper limits of what this powerful system has demonstrably produced in its past. While geologically infrequent, certain events define the upper limits of what a physical system can achieve when conditions align. To understand this, we can turn to two key reference points in Yellowstone's history. The first occurred roughly 13,000 years ago at the northern edge of Yellowstone Lake, an event of monumental scale. The second took place in 1989 at Norris Geyser Basin, witnessed by a handful of people. Though vastly different in magnitude, both are crucial for comparison, as they sit on the same continuum of physical processes that produced the eruption of April 28th. The only true difference is one of scale. The most powerful hydrothermal explosion in Yellowstone's known geological past is the Mary Bay event. This cataclysmic eruption happened approximately 13,000 years ago, carving out the arc-shaped indentation we now see at the northern end of Yellowstone Lake. The evidence of this event is a massive crater, measuring about 2.5 kilometers in diameter. By any standard, this explosion represents the empirical upper boundary for such events in Yellowstone's late Pleistocene and Holocene record. The sheer size of this feature tells a story of unimaginable power. To truly grasp the scale of this crater, imagine standing at its center. A walk to the rim in any direction would take the better part of half an hour. The crater is so vast that the bay itself, the very geographic feature that defines that shoreline today, is the direct result of the explosion. The water-filled depression we see at the lake's edge is what remains of the void created 13,000 years ago, when a huge section of the lake bed, along with everything above it, was violently blasted upward and outward. It must have been one of the most ferocious events to occur at Yellowstone in the post-glacial era. The aftermath of the Mary Bay event was equally dramatic. Geological surveys have discovered ejecta from the explosion several kilometers from its source. On the surrounding plateau, researchers have mapped blocks of rock the size of small houses that were hurled by the blast. Based on the crater's volume and the distribution of this debris, the energy released is estimated to be in the range of tens of megatons of TNT equivalent. This places the event on a scale comparable to the detonation of large nuclear weapons, a truly sobering thought. If such an event were to occur at the same location today, the consequences would be catastrophic. The destruction would radiate for many kilometers, encompassing most of the northeastern quadrant of the park. This zone of devastation would include critical infrastructure, like the Lake Village area and the surrounding road network. The ancient past here offers a stark warning about the potential for future disruption. The mechanism behind the Mary Bay event was, in principle, the same one we have been exploring. A volume of superheated water, trapped beneath a sealed cap, experienced a catastrophic failure. This caused the water to flash instantaneously into steam, and the resulting expansion drove the massive ejection. The key difference was the immense scale. The volume of water involved was on the order of cubic kilometers, not cubic meters, and the sealed region was buried hundreds of meters deep. The trigger may have been an earthquake or another major disturbance that breached the seal over an exceptionally large area all at once, unlike the slow, gradual failures that typify smaller eruptions. The recurrence interval for events of this magnitude is not well understood, primarily because the sample size is so small. Mary Bay stands as the largest documented explosion, but it is not entirely alone. The Indian Pond event, from about 3,000 years ago, was somewhat smaller, but still created a crater hundreds of meters across. Similarly, the Turbid Lake event, around 9,400 years ago, was also in this intermediate range. This raises a difficult question. How do we assess the risk of something so powerful, yet so infrequent? Based on the limited data, the best current estimate suggests that an event on the scale of Mary Bay might occur once every several thousand years. For any single human lifetime, the probability of witnessing such an event is low, perhaps only 1 or 2%. Over a century, that figure rises to a few percent. But over the span of a millennium, it becomes more likely than not, and over the next 10,000 years, it is considered a near certainty. The Mary Bay event serves as a crucial benchmark. It is the ultimate expression of what Yellowstone's hydrothermal system can produce, a real-world example from the extreme end of the distribution. While it tells us what the system is capable of, it does not tell us when the next major event will happen. The geological system, however, remains fundamentally unchanged. The caldera, the lake, and the underlying magma chamber are all in the same place they were 13,000 years ago. This means the slow, inexorable processes that built the sealed reservoir for the Mary Bay explosion are still at work today, somewhere in the system, building toward the next event in that size class. Now, let us consider the other end of the historical record, the 1989 explosion at Pork Chop Geyser in Norris Geyser Basin. Norris is a separate thermal area, located in a different part of the park from Biscuit Basin, with its own unique water chemistry and features. Before the event, Pork Chop Geyser was a small, unassuming feature on the south side of Norris's back basin, known for its regular, predictable eruptions of water. On the 5th of September, 1989, this predictability was shattered. With no apparent warning, the feature underwent a hydrothermal explosion. While minor by the standards of Mary Bay, the event was still powerful enough to hurl rocks tens of meters and launch mud and water dozens of meters into the air. It completely reshaped the geyser's surface geometry. Where a small geyser had once been, there was now a small crater. The Pork Chop Geyser, in its previous form, had ceased to exist. There were people in the basin at the time of the explosion. Although the boardwalks at Norris were not as crowded in 1989 as they are today, tourists were present. The closest individuals were about 50 meters away when the eruption occurred, and rocks landed just a few meters from them. In a remarkable stroke of luck, no one was struck by the ejector, and no one was killed or injured. The incident serves as a potent reminder of the inherent unpredictability of these thermal areas, where even small features can pose a sudden and serious danger. The sheer geometry of the 1989 Pork Chop Geyser explosion was what ultimately saved the lives of those standing nearby. For the modern era of Yellowstone observation, this incident became the quintessential example of a moderate hydrothermal blast. Before the 2024 event at Black Diamond Pool, whenever scientists or journalists needed to illustrate such an explosion, they would invariably reference pork chop. Yet, the visual record of that day is remarkably thin, consisting of only a handful of photographs taken just after the eruption and no clear video footage. This stands in stark contrast to the extensive documentation we now have of the 2024 Black Diamond Pool event and the partial record from the 28th of April, 2026, which are far more complete. While the 2024 event may have supplanted pork chop in the public consciousness, for researchers, pork chop remains the more rigorously studied of the two, benefiting from decades of subsequent analysis. The enduring lesson from pork chop is a sobering one. A significant hydrothermal explosion can occur without any identifiable warning signs, even in a basin accessible to the public. It was a stark reminder of how quickly the landscape can change. The underlying physics reveals a fascinating connection between these events. The very same mechanism that drives the small, frequent bursts at Black Diamond Pool was responsible for the Pork Chop Geyser explosion. When scaled up further, with the magnitude depending on the volume of trapped water and the strength of the geological seal, this same process can produce cataclysms on the scale of the Mary Bay craters. This suggests that there is a continuous spectrum of explosive potential, from the smallest detectable tremor to the largest event the system can possibly sustain. This continuum is not merely a theoretical concept. It is a physical reality, governed by a real probability distribution. In this light, the minor events at Black Diamond Pool are not just a local curiosity. They are vital data points, samples drawn from that distribution, showing us in real time how the system behaves at its lower end. The same natural laws that generate these small pops also, far less frequently, produce their much larger and more destructive counterparts. This spectrum of activity provides a framework for understanding the events at Black Diamond Pool. At the lowest end of the scale, we have the 2026 sequence. Events that largely occurred at night, often required sensitive instruments for detection, and only occasionally threw a few rocks into the air. In the middle of the spectrum lies the pork chop event, which produced an ejection column 50 meters high, destroyed a geological feature, and spared nearby tourists only through sheer luck. At the highest end, we find the ancient Mary Bay event, which carved out a crater 2.5 kilometers wide and blanketed the surrounding region with ejecta for kilometers. The event of April 28th sits squarely at the small end of this scale, driven by the same physics that operates at the other two extremes. The fact that all three of these scales are present in the geological record, that they are mechanistically linked as samples from a single distribution, elevates the 2026 sequence from a local anomaly to a profound window into the entire Yellowstone system. It is the system demonstrating that the forces behind the small events are the same forces that created Pork Chop and Mary Bay. In any single event, the resulting size may be a matter of chance, but the fact that these events happen at all is a matter of the system's fundamental structure. There is a peculiar cognitive trap that has formed around the public's understanding of Yellowstone, and it is worth pausing to examine it closely. This trap helps explain why a sequence like the one at Black Diamond Pool is often perceived as a mere footnote rather than a main chapter in the ongoing story of the caldera. The trap is the pervasive mental model of the supervolcano. This narrative is powerful and familiar. Yellowstone is a colossal volcano that has erupted catastrophically in the distant past and is destined to do so again. It is often described as being overdue, with its internal pressures building and its rumbles growing louder. The signs of this impending doom, the story goes, are visible to those who know where to look. In this model, the government is either aware of the coming disaster and concealing it, or it remains blissfully ignorant. When the eruption finally occurs, it will be a civilization-altering catastrophe, burying North America in ash, plunging the climate into a volcanic winter, and causing the collapse of global food systems. This is the dominant model, so ingrained in popular discourse that for many, it is the only lens through which Yellowstone can be viewed. What makes this narrative so compelling is that each of its individual components is, on its own, defensible. Yellowstone is indeed a giant caldera. It has experienced 3 catastrophic eruptions in the last 2 million years. It will almost certainly erupt again at some point in the distant geological future. And the signs of a truly impending eruption would likely involve specific patterns of ground deformation, seismic activity, and gas emissions. Furthermore, the consequences of such an eruption would, in fact, be as devastating as the popular narrative suggests. Not a single one of these pieces is factually incorrect. The error lies in how these pieces have been assembled into a story about the present moment. The critical part of the model that the public narrative has misconstrued, and the part that truly matters for us today, is the probability of a catastrophic eruption occurring within a human lifetime. The recurrence interval for these massive events is on the order of 600,000 to 800,000 years. The last one occurred approximately 630,000 years ago. While this places us within the typical range between eruptions, the variability in past intervals is too great to confidently declare that we are either overdue or safe. It's a timescale that challenges our human perspective. The best current estimates place the annual probability of a caldera-forming eruption at around 1 in 700,000. This is an exceptionally small number. In fact, among all the potential hazards listed by the USGS for the Yellowstone system, a supereruption has the lowest annual probability. It is the least likely dangerous event the system can produce in any given year. Many of the signs that the public watches for are real geological phenomena that regularly occur at Yellowstone, but they do not signify what the supervolcano model claims they do. The floor of the caldera deforms, rising in some years and subsiding in others, with a cumulative change of tens of centimeters over the last century. This is simply the normal background behavior of a large caldera system, whose underlying magma chamber exchanges fluids and gases with the surrounding rock. It is the system breathing, not a sign of imminent eruption. Similarly, the behavior of geysers changes over time. Steamboat Geyser, for instance, has experienced decades of dormancy, punctuated by years of frequent, powerful eruptions. This transition between states is not driven by new magma intruding from below. Earthquake swarms also frequently occur. These are all signs of a living, breathing, and active geological system, not necessarily one on the verge of cataclysm. Yellowstone National Park is a place of constant, subtle motion, experiencing between 1,500 and 2,500 earthquakes every year. The vast majority of these are minor tremors, often occurring in swarms that appear and then fade away. These swarms are not harbingers of an impending catastrophe. Rather, they represent the normal background activity of a system defined by immense heat flow and a complex, shallow seismic environment. Yet, a common public model interprets each of these occurrences as a prelude to disaster. This model suggests that because the caldera is rising, the geysers are changing, and earthquakes are swarming, a supereruption must be imminent. But this interpretation overlooks a crucial truth. All these phenomena fall well within the established range of the system's behavior over decades and centuries, regardless of whether a major eruption is on the horizon. The pattern recognition at play here is, in technical terms, a form of false positive, identifying a signal where only baseline noise exists. This disconnect highlights where the true risks lie. The most probable hazard in any given year is not a caldera-forming eruption, but rather hydrothermal events. These are small incidents that can occasionally escalate into significant explosions within the very basins where tourists walk, separated from active features by only a few dozen meters. Another immediate danger comes from seismic activity, earthquakes strong enough to damage infrastructure, and that have, in the historical record, caused fatalities in the regions surrounding the caldera. The most likely threats in the near term are what we should focus on, yet they are often overshadowed. The supereruption is the dramatic, worst-case scenario, but its probability is akin to a major asteroid impact, a real possibility on a geologic timescale, but almost certain not to happen in our lifetime. There is another layer to this story, one that explains why this misperception is so persistent. The same thought process that creates the public's mental model also fuels mainstream media coverage of Yellowstone. When a journalist covers a story about the park, there is immense editorial pressure to connect it to the supereruption narrative, because that is the framework that captures readers' attention. A story detailing the actual hazard rankings with precise data simply attracts fewer clicks than one about a world-altering volcanic event. The economic incentives of the media ecosystem thus reinforce the misconception. Even when individual reporters understand the science correctly, the result is a self-reinforcing loop. The public fears the supereruption, the media reports on it as the primary threat, and the public's belief is validated by the coverage. The actual, more immediate dangers receive occasional mention, but never manage to displace the dominant, more cinematic narrative. This cycle has been repeating for decades. and it will take more than a single piece of media to break it. A useful parallel can be drawn with earthquakes in California. If you live there, the most pressing danger is not the legendary megaquake on the San Andreas Fault. While that is the most cinematic version of the hazard, the truly dangerous event is the moderate quake, between a magnitude 5 and 6.5. This is the event statistically much more likely to occur in your lifetime, capable of damaging older buildings, starting fires, breaking pipes, and causing concentrated fatalities. The megaquake is a real threat that requires attention from long-term infrastructure planners, but the day-to-day hazard is the moderate tremor. People who live in California understand this instinctively, but outsiders often do not. The Yellowstone analogy is strikingly similar. The most dangerous thing about the park is not the super eruption. That is a real phenomenon, deserving of study by those who plan on timescales of tens of thousands of years. The actual present-day hazard, the one that could harm a tourist this very decade, is the hydrothermal explosion. The fact that a super eruption is more dramatic and easier to discuss does not change which danger is more likely to affect a human life. The 2024 event at Black Diamond Pool, which produced the first viral footage of a hydrothermal explosion, offered a rare chance to begin shifting this public model. However, in a structural sense, it did not succeed. The footage was largely consumed as a curiosity. The public watched, briefly searched the term, and then returned to thinking about the supervolcano. Now, the 2026 sequence presents a second opportunity, with 5 distinct events over 5 months, including one captured in clear morning light by a webcam. There is more raw material to help reshape public understanding than the 2024 event provided. Whether this new sequence will succeed where the earlier one failed depends partly on how it is framed in the public conversation. This very narration is one attempt at that framing. It will not be enough on its own, but the data has been pointing in this direction for 40 years. The empirical record now unfolding at Black Diamond Pool provides, in real time, the kind of demonstrable evidence that the data has long needed to finally be heard. There is a category of public discourse surrounding Yellowstone that warrants direct engagement rather than dismissal. This approach is necessary because simply ignoring it has not worked, and an honest examination is ultimately more interesting. This is the realm of conspiracy framing. It encompasses a family of claims, held with varying degrees of conviction, that the federal scientific establishment is concealing critical information about Yellowstone. The core idea is that if the public knew the whole truth, its reaction would be profoundly different. The most potent version of this claim asserts that the USGS is actively suppressing or downplaying data about Yellowstone's near-term hazards. The motive, under this framing, is that the economic and political fallout from such a disclosure would be catastrophic. From this perspective, the 2026 sequence at Black Diamond Pool is not a series of isolated events, but the visible tip of a much larger pattern of activity that the USGS is deliberately choosing not to fully describe. The small, publicly reported incidents are seen as euphemisms for a developing crisis at depth, one that the agency is aware of and actively hiding. The empirical case against this conspiracy framing is straightforward, and it is worth outlining because it addresses the claim without requiring the audience to simply trust the USGS. The argument is built on 3 key points. First, the fundamental data from Yellowstone's monitoring network is publicly accessible. The raw seismic waveforms from the Yellowstone Volcano Observatory YVO network are published in near real time on the USGS Earthquake Hazards Program data server. Similarly, the GPS deformation data is available for anyone to see on the UNAVCO website. This open access to raw information forms the very foundation of a transparent scientific process. A remarkable degree of transparency surrounds the monitoring of Yellowstone. Critical data streams, from satellite-based INSAR readings to public webcam footage are openly available. Even detailed information on water levels and temperatures for features like Black Diamond Pool is published on the WIO's public dashboard. This open access policy means that one does not need to rely solely on the official interpretations offered by the USGS. For those with the necessary expertise, all the raw information is there to be scrutinized and analyzed independently, fostering a system where trust is not demanded but earned through verifiable data. Furthermore, this analysis is not confined to a single institution or country. A global community of scientists, with researchers in nations like Italy, Germany, Japan, the United Kingdom, and Canada, actively studies this public data. Over the years, their published work has often presented different perspectives, sometimes arguing that certain monitoring signals are more concerning than the USGS has suggested, or that deformation patterns point to processes not fully accounted for. This open scientific discourse, with its debates and disagreements, is a sign of a healthy field. Crucially, while these independent papers challenge specific interpretations, none have uncovered evidence of data suppression or a coordinated effort to hide an impending crisis. If such a pattern existed in the data, it is reasonable to assume these researchers, who have already shown a willingness to dissent, would have found it. The historical record of the USGS's own public communications also runs counter to any narrative of concealment. The agency has consistently chosen to acknowledge uncertainty rather than project false confidence. Following the 2024 event, for instance, the USGS released a series of detailed bulletins that described the incident, its mechanisms, the changes to the pool, and the remaining interpretive questions. Similarly, during significant seismic swarms, their real-time updates have often heightened public awareness rather than dampening it. This pattern suggests a communication strategy aimed at transparency, even if the information is complex or alarming. Such a track record makes the idea of a deliberate suppression of critical information seem highly unlikely. This evidence largely dismantles the strong version of any conspiracy claim. Yet, a weaker, more subtle version persists. The idea that USGS scientists privately harbor more serious concerns than their public statements reveal, held back by institutional caution. By its very nature, this is difficult to disprove, as one can never truly know another's private beliefs. However, we can look for logical inconsistencies. The scientific literature itself provides a powerful counterargument. It is filled with a spectrum of viewpoints, including papers that adopt a more pessimistic stance than the official USGS position. If researchers held more dire views privately, the academic world would be the natural place to express and debate them, and indeed, other scientists are doing exactly that. The fact that the range of published opinions aligns with the public discourse suggests there is no vast, hidden gap between private belief and public communication. Moving beyond claims of conspiracy, we arrive at a far more tangible and pressing issue, a question of policy and ethics. Is it appropriate for the National Park Service to maintain public access to areas like the Upper Geyser Basin, given the known hazards? The 2024 event at Black Diamond Pool serves as a stark reminder of the danger. An explosion occurred on a public boardwalk, hurling rocks near tourists who were saved only by chance. While the relocated boardwalk at Biscuit Basin has since been closed, iconic locations like Old Faithful, the visitor centers, and surrounding trails remain open. These areas all sit within a thermal basin with a history of hydrothermal explosions. The decision to keep them accessible is a calculated one, based on data suggesting the daily probability of a harmful event at any specific tourist location is exceptionally small. This raises a profound ethical question, not of conspiracy, but of transparency and informed consent. Is this residual risk being communicated clearly enough to the public, allowing visitors to make a truly informed choice about their own safety? Another point of confusion, often mistaken for secrecy, is the matter of funding. The enhanced monitoring at Black Diamond Pool was made possible by emergency funds allocated after the 2024 event. However, the instrumentation across most of Yellowstone's other thermal features is significantly less dense. Some areas known from the geological record to have produced powerful hydrothermal explosions have very little modern monitoring at all. This is not a case of concealment. It is a matter of resource constraints. In its own budget requests, the USGS has publicly made the case for expanding this monitoring network. The agency itself states a preference for more comprehensive data. Whether that funding is granted is ultimately a political decision made by Congress, not a scientific one. Finally, it is worth reflecting on a broader phenomenon in our collective consciousness. Yellowstone has become more than a national park. In the public imagination, it serves as a powerful symbol for impending catastrophe. It is a canvas onto which a range of modern anxieties about climate change, the fragility of our institutions, and systemic collapse are projected. The narrative of a civilization-ending super eruption fits this symbolic role perfectly, offering a geologic metaphor for the end of an era. The more localized, albeit still dangerous, threat of a hydrothermal explosion does not carry the same symbolic weight. It represents a specific, contained hazard, rather than the all-encompassing cataclysm that Yellowstone has come to represent in our cultural storytelling. When the public dialogue turns to Yellowstone, it often carries an undercurrent of something more than geology. The idea that an eruption is overdue, or that authorities are concealing the truth, can be an expression of deeper societal concerns. These narratives sometimes reflect a general mistrust of institutions, a pervasive anxiety about long-term risks, or a feeling that vital information is being withheld. To properly address these conspiracy frameworks, one must first acknowledge the anxieties that fuel them, engaging with the underlying unease even while presenting the correct geological facts. And yet, this does not alter what the scientific data reveals. For Yellowstone, a super eruption represents the least probable event in any given year. Far more likely is a hydrothermal explosion or a sequence like the one observed at Black Diamond Pool in 2026. Such events appear on our instruments and webcams in real time, offering a chance for public engagement with the data as it happens. The central question is whether the public chooses to see this activity for what it is, or simply processes it as another verse in the familiar, dramatic song of a looming super eruption. To place these events in their proper perspective, we can embark on a brief survey of other hydrothermal and shallow volcanic systems around the globe. This global context is invaluable, as it helps us distinguish which patterns at Yellowstone are unique and which are simply the characteristic behavior of the kind of geological system it is. This comparative journey reveals a fascinating story about our planet's restless nature. Since 2021, Iceland's Reykjanes Peninsula has been in a particularly active phase. The Fagradalsfjall and Sundhnúkar eruption sequences have generated multiple effusive eruptions across the peninsula's volcanic systems. This activity has impacted a town, damaged a road, and produced a level of small-volume volcanism in a densely populated area that Iceland has not witnessed in centuries. While Reykjanes is a different type of system, a mid-ocean ridge emerging above sea level with frequent basaltic magmatism, unlike Yellowstone's continental rhyolitic caldera, it shares a high heat flow and a geologically young, active character. What is happening there is simply what Reykjanes does on multi-century timescales. The current activity is significant, but not without precedent in the longer geological record. Notably, the public discussion in Iceland has remained more grounded, partly because the system is a visible part of daily life, and partly because the warning systems have proven effective, allowing residents to see the data for themselves. Meanwhile, in New Zealand, the Taupo volcanic zone has also displayed elevated thermal activity across several features in recent years. This zone extends north-northeast from the central North Island and encompasses Lake Taupo itself, a caldera whose scale is comparable to Yellowstone's and which has produced enormous eruptions in its own geological past. Several of the zone's geyser fields have exhibited unusual behavior, and the alert levels for specific volcanoes have fluctuated. Here, too, the public conversation has been measured, with New Zealand's monitoring agency, GNS Science, communicating effectively to distinguish between routine variations and more concerning signals. It is a crucial point that despite the heightened activity at individual features, the system as a whole is not considered to be in a state that suggests an imminent caldera-forming eruption. Perhaps the most concerning of the global parallels can be found in Italy. The Campi Flegrei caldera, located west of Naples, is undergoing a phase of sustained ground uplift that has now continued for more than a decade. This uplift, along with an increase in both the rate and magnitude of seismic activity, has ignited a vigorous scientific debate. Are these signs that the system is approaching an eruption? Or is this an extended period of unrest that will eventually resolve without a magmatic event? In response, the Italian Civil Protection Authority has raised the alert level for Campi Flegrei and has started preparations for the potential evacuation of populated areas within and around the caldera. The case of Campi Flegrei is especially sobering because of the large population at risk and the unambiguous, sustained nature of the uplift. Yet, it also serves as an example of transparent communication, with Italian authorities providing detailed public explanations for the alert level changes and what they might signify. Beyond these major examples, smaller parallels exist across the planet. The Long Valley caldera in California has been closely monitored for decades and has experienced its own episodes of unrest. Italy's Phlegrean fields have an even longer recorded history of unrest than the current Campi Flegrei episode. And near Taipei, the Tatun volcanic group shows periodic seismic and thermal activity. Each of these systems, much like Yellowstone, produced massive eruptions in the deep past and is now monitored with varying degrees of intensity, reminding us that we live on a geologically dynamic world. Taken together, this global survey reveals a fundamental truth. Hydrothermal and shallow volcanic systems are, by their very nature, unsettled places. They generate small events at regular intervals and can enter periods of elevated activity that last for years or even decades before subsiding without a major eruption. The empirical record shows that the probability of any single period of unrest escalating into a larger event is modest. However, the probability that times such period, somewhere times on Earth, will eventually escalate over a long enough time window is much higher. The honest scientific approach, therefore, is to monitor these systems closely, treat any unusual signals with seriousness, and accept that the vast majority of unrest episodes will resolve peacefully. So, what are we to make of the apparent global pattern of multiple systems showing elevated activity at the same time? This is most likely a function of two factors. First, these volcanic and hydrothermal systems are in a constant state of flux, meaning that at any given moment, a subset of them will naturally be in a more active phase. The fact that a survey in 2026 finds several such instances is not, by itself, evidence of a global synchronizing trigger. Second, our ability to see this activity has been transformed by decades of increased global monitoring. A system in an elevated phase today is detected and reported. 50 years ago, the very same system might have exhibited the same activity without anyone noticing or reporting it publicly. It raises the question of how much our perception of risk is shaped not just by the planet's behavior, but by our ever-improving ability to watch it. A portion of what appears to be a global pattern of activity is, therefore, more of a detection artifact than a genuine synchronization. The reality of the Black Diamond Pool sequence, when viewed in a global context, is far more grounded. Hydrothermal systems, by their very nature, are in a constant state of subtle unrest. What makes Black Diamond Pool special is not a unique rate of activity, but rather the density of scientific instruments that allows us to measure that activity with such precision. This shifts our perspective from a synchronized planet to a well-observed corner of it. Similar kinds of unrest are occurring at various intensities in thermal areas across the globe. The sequence at this one Yellowstone pool is simply a local expression of a universal category of behavior, a manifestation of physics that operates identically wherever the right mixture of heat, water, and shallow plumbing is found on Earth. With this understanding, we can now look ahead and consider what the next 12 months are likely to reveal and what questions the public should truly be asking. Based on the available data, published interpretations, and the ongoing assessments from the Yellowstone Volcano Observatory, an honest, forward-looking statement can be made. Over the next year, the most probable trajectory for Black Diamond Pool is a continuation of small events. The conduit modification theory predicts that this elevated rate of activity will persist for a time before gradually decaying as the pool's plumbing system re-equilibrates. The duration of this decay could span months or even years, a timescale supported by published literature on similar post-event sequences at Yellowstone and elsewhere. We should anticipate several more small events at Black Diamond Pool in the coming 12 months, each detectable by the sensor network and some visible on webcams, all contributing to the empirical record. It is important to note, however, that we should not expect any of these events to be dramatically larger than those already seen in the 2026 sequence. The most probable path does not include a pork chop scale event or larger at this specific pool within the next year, though the probability, while low, is never zero. For the wider Biscuit Basin area, the most likely scenario for the next 12 months involves the continued closure of the relocated boardwalk. If the basin reorganization scenario proves correct, it would imply that detectable changes could begin to appear at other thermal features over the same period. The sensor network is diligently watching for just such a development. Should changes at other features emerge, the boardwalk closure could be extended or even expanded. Conversely, if no new changes appear and the activity at Black Diamond Pool either stabilizes or decays, a reopening could be considered at some point. This decision will ultimately be made by the Park Service, in consultation with the USGS, based on monitoring data and a thorough assessment of any residual risk to visitors. For the park as a whole, the next 12 months should look much like any other year. As we have discussed, the annual probability of a pork chop scale or larger hydrothermal explosion occurring somewhere in the park is on the order of 1 in a few decades. This means that in any given year, the chance of such an event is roughly 1 in 20 or 30. To understand the actual risk to a person, you must multiply that by the probability that the event occurs in a basin open to tourists, with a boardwalk geometry where ejecta intersects with visitor locations. This is where statistical probability meets the reality of a visit to a geologically active landscape. The resulting probability is small, but it is not negligible, and over a long enough time frame, it accumulates to a near certainty. The real question is whether, when the next event happens, the basin in question has had its monitoring upgraded as Black Diamond Pools has, and whether that data is being processed in a way that could offer even a few seconds of warning. This brings us to the heart of the matter, which is not whether the supervolcano will erupt. On geological timescales, it eventually will, but it will almost certainly not erupt in your lifetime, nor in the lifetime of your great-grandchildren. The annual probability is so small that you are vastly more likely to be affected by the dozens of mundane causes that constitute human mortality. The supervolcano is not the question for our time. The true question is whether, the next time you visit Yellowstone and walk along a boardwalk past an active thermal feature, That system happens to produce a moderate hydrothermal explosion on that day. The probability of this happening on any single visit is small. Yet, when that probability is integrated across all visitors and all visits over decades, it becomes much larger. It is a stark reminder that probability, given enough time, will explore every possible outcome. Some number of times over the coming decades, an event of that size will occur somewhere in the park while tourists are present. The geometry of how the ejecta intersects with those tourists will be a matter of pure chance. Some of these events will produce no injuries, others inevitably will. Over time, the roll of the dice will eventually produce a bad outcome. The events of April 28th, the 23rd of July 2024, and the pork chop event of 1989 are not anomalies, they are warnings. They represent the small and medium samples from a distribution that will, at some point and at some location, produce a sample from its larger end while tourists are present. This is the threat. It is real, it is well characterized, and it is the second most likely hazard category at Yellowstone, surpassed only by large earthquakes. It is the very thing the data has been pointing to for decades, and it is what the 2026 sequence is in its own quiet and persistent way, making visible to us all. A parallel may help to frame this risk more clearly. Consider how the public thinks about lightning. In the United States, lightning kills an average of around 20 people per year. The probability of being struck on any given day is extremely small. And yet, when a thunderstorm approaches, people who have grown up in lightning-prone areas know to come inside. They avoid standing under tall trees or in open fields. Through cultural transmission and direct experience, they have developed an accurate intuition about the modest but real hazard that lightning represents. They do not fixate on the dramatic outliers, like a storm that destroys a city or a rare cluster strike that kills multiple people at once, because those outliers are not the typical hazard. Perhaps we need to cultivate a similar, more nuanced intuition for the geothermal landscapes we treasure. Our perception of risk is often shaped more by drama than by data. On any given day, the danger of a lightning strike is a familiar concept, a single bolt finding a person in the wrong place at the wrong time. Our cultural intuition for this kind of hazard is well adjusted, yet our understanding of Yellowstone is not. It is calibrated to the spectacular outlier, the caldera-forming supereruption, rather than the park's most common hazard, the hydrothermal explosion. It raises the question of what it would look like if our perception aligned with reality. If such a shift were to occur, visitors might view the park's boardwalks differently. They would understand that these paths are not entirely without risk, that the geothermal basins have a history of consequential events and will inevitably produce them again. They would grasp that a modest, residual danger is real, and that by entering the park, they have implicitly accepted it. This perspective would mirror the way Floridians regard thunderstorms, with a healthy respect for the hazard and an awareness of its nature, but without constant fear, because the daily probability is low. In this corrected view, the fixation on a supereruption would fade, much like a beachgoer in May doesn't dwell on a once-in-a-century hurricane. The recent events of 2024 and the sequence in 2026 provide the most powerful data in decades to help correct this deep-seated misconception, though whether this correction will take hold remains to be seen in the public discourse of the coming years. If you were to allocate your sense of concern about Yellowstone in a way that truly responds to the data, your focus would shift dramatically. It would move away from the supereruption, away from the imagined ash cloud that may or may not blanket a continent. Instead, your attention would settle on the boardwalk you might be walking on, the basin you could step into, or the tranquil pool you pause to admire on a day when the conduit beneath it happens to rupture. You would notice that the boardwalks at Old Faithful are designed with an accepted level of risk, and upon visiting, you would accept it with full awareness. You would see that in the period after 2024, the National Park Service and USGS have invested heavily in monitoring one particular pool, and you would understand the reasons for this focused attention. This same logic would suggest a need for more monitoring at other features across the park, a decision whose budget is ultimately determined by Congress. In short, you would begin to see Yellowstone as the data shows it to be, not as our collective imagination has constructed it. And then, when a webcam at Black Diamond Pool captures another event one morning, as it almost certainly will, you would know what you are witnessing. It would not appear as a sign of impending catastrophe, or as evidence that a supervolcano is stirring. You would not see it as a minor footnote to the grand story of an eruption that is unlikely to occur in any meaningful human time frame. Instead, you would see the event for what it is, a small, natural expression of a vast geological system that has been operating for hundreds of thousands of years. It serves as a quiet reminder that the most tangible danger in this place is not the dramatic event in our imagination, but the modest event recorded in the data, a single pool in a basin, exploding on a clear morning. The true threat of Yellowstone has, in a sense, been erupting all along. For hundreds of thousands of years, these hydrothermal events have been a constant feature of the landscape. They have occurred on quiet boardwalks in front of webcams, at night beneath a cover of ice, in basins we have never closed to the public, and in those we have. These small explosions represent one end of a broad spectrum of activity. A distribution that at its most powerful has carved bays into lakes and reshaped entire quadrants of the park. This is simply what the system does. It is the part of the system we have, until very recently, looked past while on our way to contemplate a part we have almost entirely imagined. The observation will continue. The webcam will keep its vigil, the sensors will keep recording, and the pool will keep refilling. Sometime in the next year, a sixth event will likely occur, followed by a seventh and an eighth. Each one will be entered into the record, meticulously analyzed, and will tell us a little more about a system that every year, every month, every Tuesday morning, is doing exactly what it has always done. The system is dangerous. It has always been dangerous. But it is dangerous in a specific way, on a specific scale, and in a specific kind of place. The enduring question for us, the ones watching, is whether we can finally see it for what it is. Not the imagined catastrophe, but the real one, the one that is already happening.